Ladies and gentlemen, please welcome to the stage Apigee CTO Anant Jhingran.
Hello, everyone. Hello, everyone. Good morning. It's absolutely fascinating to be here today, and I hope you guys had a great time yesterday. I got a chance to talk to many of you and attend a few sessions. So I both learned a lot from the sessions as well as in interacting with all of you, and I hope so did you. Today is going to be slightly different. Today, we are going to talk about some technology. And before I kind of get there, let me kind of warn you that I've been accused of being slightly professorial. And normal human beings would say, since that's an accusation, let's try to tamp it down. But I'm not a normal human being, so I'm going to actually amp it up. There will be questions that you have to answer correctly. There won't be any homework. The second thing that I want to just tell you is that I tend to kind of walk around. And yesterday when I was walking around, I kind of came living on the edge pretty close. So people got really scared. So there were some chairs here. So the things have been moved off. But if you find some people screaming in the front, it's because they think that I'm about to fall off. And we'll try to remove that excitement from the talk here. So yesterday, in the keynote by Chet, and then on a wonderful panel that followed after that, we talked about being digital. And we talked about how being digital means to have the right culture, to have the right community, and have the right code. And then the panel that followed, the keynote, there were some wonderful discussions on culture and community. Today, we are going to take a deeper dive on code. Okay? Think about this as kind of CS 101. And we are going to walk through some software principles that will actually help all of us, that have helped Apigee, and that will help all of you be digital. I'm doing a wonderful job staying behind this line. So the main theme of what I want to talk about is what got you here won't get you there. Or as Chet put it, the old will not take you to the new. Now, we love the apps that sit on these phones. They're really beautiful. Great experience. Most of the apps that we have 4-star or 5-star rating. But we, as technologists, understand that really what makes these apps run is great systems behind them. Systems that have many components, but for the purpose of this discussion, I'm going to focus on 3. Computation and logic, data, which includes persistence, analytics, and operations. What I'm going to assert is that companies that have come up in this new digital world have actually put in some fundamentally different software architectures. They believe that these software architectures actually give them a competitive advantage. They believe that these software architectures allow them to be agile at scale, efficient at scale, and intelligent at scale. The 3 things that Chet had talked about as the competitive advantage from code. The question for all of us, including the digital natives, is, what do we need to do to actually adopt these principles? How do we actually adopt these principles so that we can actually compete in this fast-changing digital world? What I'm going to do is kind of walk you through what the right looks like, give you some examples of what the right looks like, and give you a potential path to go from where you are to where you need to be. So you're there with me? Great. Be prepared for some questions, though. Technical questions, not just, is the world great and all that stuff. Okay, so you thought that Anant will stand up and talk about cloud and big data and mobile. You guys get it. We get it. We are here. We believe in the power of these technologies. I'm not going to bore you with stuff that you already know. I'm also not going to talk to you about technologies that are just coming up. Who can say what this technology is? Sorry? Blockchain, exactly. Today you can basically get this technology if you go to a hardware store. At some point in time, this technology will actually make it to the mainstream. But I'm not going to talk about technologies that are riding the hype curve. I'm going to talk about technologies that have established themselves as kind of the core foundational principles for how new modern digital software is built. So we'll walk through 5 software principles, and there are many more, and let's go through them one by one. The first software principle, of course, is scalability. How do you do scalability? So think about an app that is communicating with a server and updating a counter. You didn't expect to hear a talk about updating a counter here. But yes, think of an app that is going there and updating a counter. Now think about that same thing happening 1 trillion times a year. You say, okay, no problems. Chet's talked about how apps are actually multiplying. The number of people who are coming online, what did Chet say? Maybe 1,000 a second or 1,000 a minute or what else it is. So no problems. Scaling on the left side is somebody else's problem, and that's growth of business, so that's great. Scaling of communication is also relatively straightforward. Internet doesn't have bottlenecks. And if internet doesn't have bottlenecks, at most you have to pay for some more bandwidth. What you have to worry about is scaling the back-end servers. So assume for a minute that you can do 647.13 calls per second with a server. Dennis? Where's Dennis? Dennis, how many servers do you think I need? Oh my God, in spite of being a Seattle Seahawks fan, he's actually really smart. The answer is 49. Okay? So well done, well done. And in fact, he didn't know what the question was. Thank you, sir. So you have got 49 servers that you need to actually put in place. I had to do some divisions and all that yesterday. And I said, should I give a 10% boost for peak capacity? I said, I'll leave it at that. That'll be too much for Dennis to calculate. So, but then you run into this. Dennis said he'll laugh if the joke is good. We'll find out whether he laughed or didn't laugh. But now, you say, what should I do about this variable? Because once I do 49 servers, some traffic is going here and some is going there, and it's all great, except that pesky little counter. What do I do with it? So I put that counter in one place, and that becomes the bottleneck. So you say, okay, no problems. Let me put counters in multiple places. Some requests, Anant's requests go here, and Dennis's requests go there, and all is fine, except the counters can go out of sync. In traditional systems, you have solved this with expensive two-phase commits. You ensure that the value is the same in multiple places. If you update it in one place, you have to update in other places, and then you have got to do this dance. Did you get it? Yes, I got it. Are you ready? Yes, I'm ready. Shall we commit? Yes. Oops. No. Okay? So what you have done is you have imposed the overhead of coordination in every update transaction. Works fantastic. I built this in DB2 land. Works fantastic if you're doing 1 million transactions a year. If you're doing 1 trillion transactions, the way we want to do it for all of you, the way you want to do it to be a digital company, this will not work. An alternative is what's called eventual consistency. And what eventual consistency says is that I go and update the variable y here, and Dennis goes and updates the variable y here. And then when I update it, tung, 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 it goes to the other place. And when Dennis updates it, it goes tung, 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 tung to this place. But both of those happen out of band. And what you've done is you've taken the overhead of coordination in line to something that happens out of band. Now, of course, you run the risk of some conflicts, but you assume that the probability of conflicts is low. Because we want to handle trillions of calls for you, we wanted to ensure that we didn't have any of these coordination bottlenecks. That's why we chose Cassandra as the technology, because Cassandra supports eventual consistency. So across the 18 data centers and 7 or 9 geographical regions that we exist in, we had to build in eventual consistency. Otherwise, we would not have been able to support the request volume that you wanted. And as we give you the software to run on premises, you would not be able to support it. Let's take a second example, even funner. Reliability. How many times have you guys gone to a website and said, please enter the credit card information? And then just before you hit the submit, it says, please make sure that you hit the submit button only once. Because if you hit it more than once, your credit card may be charged more than once. So you hit the submit, and now the wheel is rotating. And now you are confused. What the heck should I do? Should I kill the browser? Should I go somewhere else? Should I go and so you say, okay, what the heck, man, systems are reliable. You assume it all happens, and the gift doesn't show up for your spouse, and she's mad, and it's all been bad. This happens because where you are sending the request from, the communication and the servers are all unreliable. How do modern systems tackle reliability? So we're going to go on a small journey, a journey to the Byzantine Empire. In the Byzantine Empire, there was a small kingdom. I'm going to take some liberty with the narrative. I'm going to make it political also in a minute. There's an empire with a small army, and the army is split across 2 hills, and they're being attacked by a larger army in the valley. The smaller army can beat the larger army, provided there's an element of surprise, and both attack at the same time. The 2 smaller armies have 2 generals, the Republican general on the left and the Democratic general on the right. Now they have to agree. And so you know this story is not going to end well anyway, right? But let's kind of go through the story and see what happens. So, no problems. The red general says, I'll wave a green flag to attack. But what happens? If you wave a green flag, the army below actually sees, so the element of surprise goes away. You wait for nighttime. Fantastic. The element of surprise is there. But now you have no mechanisms for communicating. Because now, if you light a torch, then again, the element of surprise goes away. So the red general says, okay, I'm going to take my best horseman, and I'm going to tell him, attack at 10 p.m., and please go across and communicate to the blue general. So at dusk, the horseman starts, and the general on the other side is waiting. So it is now 9. Denise, should the general attack?
Sure.
Oh my God! Okay, you're showing your Seattle Seahawks roots. The answer is no, because he doesn't know what the other guy is doing. Finally at 9:30, the horseman, beaten up, shows up and says, General, at that time the horsemen were very friendly with the general. He said, General, you have no idea what happened. I was going here and I was attacked and I went through crocodile-infested waters and this and that. And general says, shut up. Tell me, should I attack or not attack? And he says, attack. So a general says, wow. And he tells his troop, let's. And then he stops. Do you think he should attack or not attack? Anybody? No. I've always, people who use Apigee technology are very smart. The answer is no, because if he attacks, he actually doesn't know whether the Red General will attack or no. You think, what? Didn't the Red General just send a message over to attack? He did, but he actually doesn't know that the Blue General got the message. If he doesn't know that the Blue General got the message, and if he attacks and the Blue General hasn't gotten the message, then the poor Red Army is going to get, Red General's army is going to get massacred. So the Blue General says, okay, I'm going to solve this problem. I'm going to send my trusted horseman over to the Red General's side and let me convey to him that, look, I understand and I'm ready to attack. The same problem repeats itself on the Red General's side. And in fact, as you guys think through this, you will come to the conclusion that there's no way in the presence of uncertainty for the two sides to actually agree on what to do. And guess what happens? So therefore, they wait and wait. One night comes, the second night comes. Eventually, they starve to death, and they're taken over by the army in the valley. So how do modern systems solve, how do current systems solve these problems? Reliable message queues. If you're going to send a message over, it's like sending a small army along with that horseman. Let's protect that message, and let's make sure that that message doesn't get destroyed. But if you think about it, if you can actually send an army with the horsemen, that army can actually defeat the larger army. So what happens in the context of these expensive message queues is that the cost of building and reliability sometimes is extremely, extremely expensive. But if the Red General had listened to my talk, or I was actually a student of probability, he would have realized that the probability of, he could have figured out the probability of his best horseman to make over, to go to the other side, is 9 in 10. And if he sent 10 horsemen, the probability that they actually reach the other side is 1 minus 10 to the minus 10, which is approximately equal to 1. So he could have used the laws of probability and replicated the horsemen and solved the problem. And in fact, if that happened, the Blue General didn't even have to respond back to the Red General because it was almost guaranteed that he got the message. So modern systems solve unreliability through replication. I know this was a long detour, but the problem itself was absolutely fascinating. Modern systems solve the problem of reliability through replication. That's why, for example, we use Cassandra and HDFS, where we know that the underlying servers and underlying systems are unreliable. But by doing the same thing multiple times, you significantly increase the odds of you succeeding. But that's not enough. Remember the example that I gave with your credit card and your spouse getting mad at you? In reality, what the server should have implemented is what's called idempotency. What idempotency is all about is the fact that if the same message happens and comes multiple times, it is as good as it comes exactly once. For example, if you are sending a counter value and saying set the counter value to 100, it's an idempotent operation. It doesn't matter how many times it goes, the value stays at 100. But if you're going to increment the counter value by 1, then there's a random chance, if you're going to send this same message 10 times, that the counter value may be 1, 2, 3, 4, or incremented by up to 9. So true software reliability requires replication from the sender side and implementation of idempotency on the server side. So as you all think through the services that you are implementing, please do not forget that the cheapest way to implement this is a combination of replication and idempotency, and you have to do the work, hard work, in order to make your services idempotent. Let's take a third example. Here, can we get the... So let's take a third example. The third example is about unknown threats. In today's world, we have gone away from these are the good guys and these are the bad guys. You gave the keys to the good guys and you kept the keys away from the bad guy. I'm coming closer here, I know. So that's a known threat, exactly. Thank you, Greg. Absolutely. So I just want to connect with the audience. Okay, so it's quite simple. The world of known threats and unknown threats has kind of meshed in between. All of you have websites, and you want Googlebot to come into your websites. What is to prevent somebody else from pretending to be a Googlebot? Let's give you an example here. Think of two traffic patterns against your broad swath of URIs. It could be your set of APIs, it could be your content, it could be anything else. And look at the volume around it. It's entirely possible that the traffic on the left represents somebody who's trying to steal your passwords. And it's entirely possible that the traffic on the right is somebody trying to scrape you for your content. But you actually don't know. So you say, okay, let me try to start to write some rules. What rule would I write? I write a rule which says, if the volume of traffic is high, then it's likely to be a bot. But then you say, oh my God, the activity on the left and the activity on the right actually represent high volume because the area under the curve is the same. You say, okay, let me put a threshold. Now, what threshold should you put? You don't have a clue what threshold you should put, so you put some threshold. And you say, okay, if the volume is high and there's a threshold on certain URIs, it's likely a bot. And then suddenly the test department in your organization comes and screams at you and says, what have you done? We are running tests. So you say, okay, if the volume is high and there's a threshold and it is not a test department, and if it is really associated with certain sets of OAuth keys, et cetera, then it's not likely a bot. So you see what's really going on. You are taking your intelligence that is encapsulated in your brain and converting it into software. You're writing how you think into a set of programmatic code. Not going to work. Not going to work. Quite simply, the rules will become crafty, they'll be impossible to figure out, and over time, they'll be hopelessly out of date. The real way to do this is by using the power of data and the power of machines. Machines have the ability to sift the signal from the noise much better than humans can programming through the rules. So today's modern internet architectures use machines to augment human intelligence in certain tasks that are better done by human beings. And I gave an example of this malicious threat detection as a task that is much better done through machines. And that's why, for example, when we announced our Apigee Sense, it is actually built on data-driven intelligence on this side. Let's talk about a fourth example, a set of cooperating services. Now, we all know that when you send a request from here to a server, the server, as Chet also pointed out, the server doesn't just return be done. In general, there's a set of coordinating processes that go back. In today's system, this coordination happens through ESBs and message brokers. You put stuff in, and you take stuff out. You may have a mux demux of message broker. Works very well for 1 million transactions. For 1 trillion? No. Internet How do you think the internet works? Does the internet work on an ESP architecture? Does the internet work where all traffic goes to Bermuda as a message broker, and then it comes out from there? Absolutely not. The internet works as a completely distributed peer-to-peer network. You have to think through what it means for you to actually build these kinds of architectures for your key stuff. We at Apigee, for example, have built out Riemann as our monitoring and alerting system that is built completely on this distributed peer-to-peer architecture. The fifth example that I wanted to give was an example on operations. The 49 servers that I put in, Dennis can count till 12. Some of Seattle guys are very fascinated with 12. So Dennis puts in another 12 servers, and somebody else puts in some others. He's not laughing, so he'll kind of, we'll see. Because they're not doing that well this year. Absolutely. So you put in your bank of servers, and then your servers start to fall sick. In today's world, you've got an expensive Oracle transactional system running on that server. That server better not damn go down. You take care of it, you revive it, and you revive it again. In the modern world, see the pun out there, not rip and replace, but RIP and replace. In the modern world, you actually yank the server out, and they are just disposable quantities. So for example, at Apigee, the way we handle hundreds of billions of calls for you is by not taking care of the servers and patching them. We only care about keeping the service up and running, and the servers are absolutely disposable. That's the reason why we are able to actually operate at the scale that we operate for you without doubling, tripling, or quadrupling our operational staff. So I talked about these 5 examples. There are many more. I'm not saying that you have to adopt all of them. I'm not even saying that you have to adopt them the way some of these digital natives have adopted them. But I think it's really important to understand what weapons you are bringing to the table, okay? And you have to really understand how you are able to actually leverage some of these principles. But wait. I thought I'll wear a turtleneck for this, but then my wife said, I'll make an ass of myself, so I didn't wear a turtleneck. But then by saying that I didn't wear a turtleneck, I've still made an ass of myself. So I kind of got around my wife's dictum out there. You must have been wondering, in all of this talk, where are APIs? All modern systems, whether they do new forms of computation, new forms of data, new ways of operations, all modern systems work and run on APIs. They are API first. The backend systems connect with each other through APIs. The big data systems connect with APIs. The system of systems connect with APIs. In fact, enterprises connect through APIs. APIs is the 4th foundational principle, not just new computation, not just new data, not just new operations, but API first is the 4th foundational principle that modern systems are built on. We at Apigee strongly believe in many of these. In order to talk about how Apigee practices these principles, I want to call upon stage our second CEO, Shankar Ramaswamy. He is our Chief Engineering Officer. Shankar, welcome.
Thank you, Anant. First of all, I want to thank you all for being here and supporting us and making time to come listen to us. Thank you. If you've been sitting here for the past half hour or so and listening to Anant talk about these things, you might be thinking, man, what a lot of theoretical mumbo jumbo. After all, he did fess up to being the mad scientist, right? Right. By the way, how many of you loved his sound effects of the data moving along from Dennis to Dennis? I thought that was brilliant. That was brilliant, man. All right. So what I wanted to do was really talk to you about how we at Apigee practice these principles. As the person responsible for delivery of all of our products and services at Apigee, these principles are near and dear to my heart, right? And I wanted to share our journey on using those things so that hopefully you feel good and confident about using them yourselves, right? So this is not just something we're talking about, we're actually practicing it. So over the past few years, what has happened is our traffic has really taken a fairly significant turn up, right? We've got an exponential growth curve, which is great. But we've also, during that time, done something with our availability. We've actually tracked down every single call that comes to us, seeing what happens to it, and measuring and fixing issues so that we get better and better. And today, we're at 4 nines of availability, over 4 nines of availability. Now, as you can imagine, this has been a pretty hard journey. To think about the complexity of this and put this in perspective for you, imagine a jumbo jet on a steep climb, right? Jumbo jet's a big freaking thing. It's on a steep climb, pretty hard thing to achieve. And now imagine you're re-engineering the engines and the systems of that jumbo jet as it's on that steep climb, right? That is the kind of engineering challenge that we've been through these past few years. And we could not have done that without following a lot of the principles that Anant talked about. Things like eventual consistency, things like building a lot of redundancy, embracing failures, right? And planning and working through failures. All of those things are extremely, extremely important. Otherwise, we could not have done this. Now, let me talk a little bit about, it's not just that we've done the availability stuff, but we've also been innovating and delivering features to all our customers during this period, right? So it's not that we've only done the availability and nothing else. We've actually also been able to do this. And again, a lot of the same principles have come into play where we do continuous deployments. So we deliver to our cloud every 2 weeks. So we've been delivering dribs and drabs of functionality. That's how we can keep the availability up. We don't want to make big changes at once. We've also been delivering to our private cloud customers patches and, fixed packs and incremental releases throughout the year. And that's how that's one of the things that's allowed us to both reduce the time from when we develop something to get it out to our customers, but also do it in an incremental fashion that allows us to not have these big bang changes. Let me talk a little bit about the API-first approach and how we've taken that. We've always taken an API-first approach to delivering our products. All our products have APIs, of course. We're the API company. But one of the things that we're doing now is starting to use APIs internally ourselves to build our products. So a lot of these products, as you can imagine, they're not big monoliths. There's lots of things going on. And so all of those things are also being built as APIs. And that way, we get to live in your world, right? So our world looks exactly like your world. And we're able to do things the same way that we would expect you to do things. This sort of dogfooding allows us to build things where all our engineers are actually living the same in the same world as your engineers, right? And so that allows us to build products much better that are hopefully much more usable and friendly because there's no difference between what you're doing and what we're doing every day, right? Now, a lot of you have taken advantage of these APIs already, our external APIs. and you've integrated it within your own tool chains. As we start doing more and more with APIs internally, we will expose a lot of those things to you as well so that you can now do more extensive customization, more extensive extension on top of our platform. And not only can you as a customer do it, but partners will be able to build things that they can give you that might speed your implementations up as well. So that's sort of the journey we're on. So again, in summary, what I wanted to share is that these principles are real. They are something that we live each and every day, and our faith in them just goes stronger over time because we're able to do things that we could not have done had we adopted some of the legacy principles. Anant, back to you.
Thank you. Okay. I will. We've got a panel. I'm going to get back to you. Okay.
All right.
So we talked a lot about things on the right. What are the modern software principles? I gave you some examples of how things are done differently. Things are done differently. And the question is, how do you actually get there? Obviously, you have to believe in them. But we actually believe that adopting an API-first approach helps you get there. It helps you get there in two ways. The first way is that it actually allows you to shield any of the back-end changes that you'd want to do, any of these new software principles that you want to adopt from the interfaces that are associated with the people and the applications that are interacting with you. So API first is a wonderful, wonderful way to actually get on this journey towards these new software principles. But the second path is equally powerful. Because API-first technologies, such as Apigee's, are actually built on these software principles, it allows you to run some of your capabilities in and around those architectures. So you are able to actually bring in these new software principles into your enterprise and actually build upon it, build in it, and build around it. You have no choice. You have to do it. The competition, the people who are competing with you, are competing with, as Chet pointed out, agility at scale, efficiency at scale, and intelligence at scale. You have to get there. We can help. Thank you very much, folks.